Now, in this lecture, we'll find out the area of the circle. In the drawing, we have quadrilateral ABCD. Beside this quadrilateral, we have the circle. You know that side AB equals to 2 units in its length, side BC equals to 8 units in its length, side DC also equals to 8 units in its length, angle DCB equals to 90 degrees, and this angle ABC it is also equals to 90 degrees. Our mission is to find out the area of this circle. So first of all, we'll do a construction. We extend side DA and side CB until they touch each other. We define the touching point of the two sides of each other as M. CB it is absolutely a straight line because it is one side of quadrilateral ABCD. When you extend the straight line CB by straight line, the result must be a straight line. So CM it is also a straight line. So if we focus on the upper side of the straight line MC at point B, the sum of the angles here must be equal to 180 degrees. Which angles we have here? This angle equals to 90 degrees. Plus the missing angle, in total they must be equal to 180 degrees. Therefore the missing angle here must be equal to 90 degrees according to the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. We define angle A and B as theta. In the small triangle A and B, the small right triangle A and B, this angle equals to theta, this angle equals to 90 degrees. Therefore, this missing angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta it is 90 degrees, and 90 degrees plus 90 degrees it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, in the big triangle DMB, this angle equals to theta. This angle equals to 90 degrees. Therefore, the missing angle must be equal to 90 degrees minus theta for the same reason. In the next step, we will prove the big triangle DMC, the big right triangle DMC is similar to the small right triangle AMB. So I write it down. The big triangle DMC is similar to the small triangle AMB. So why the two triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. So angle DCM in the big triangle equals to angle ABM in the small triangle. They are both equal to 90 degrees, therefore they are equal to each other. I'll repeat again. Angle DCM in the big triangle equals to angle ABM in the small triangle. They are both equal to 90 degrees, therefore they are equal to each other. In addition, this angle theta, is a common angle that belongs to both triangles. Therefore, angle theta equals to itself. So, angle theta can be called as angle DMC, and it belongs to the big triangle. DMC is equal to angle theta can be defined as angle AMB when related to it as it belongs to the small triangle, angle AMB. Repeat again. Angle DMC, that is actually angle theta, equals to itself, to angle theta, that it can be called also angle A and B. Angle theta is a common angle that belongs to both angles, therefore angle theta equals to itself. And finally, those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. So we can write down that angle MDC in the big triangle equals to angle MAB in the small triangle. They are both equal to 90 degrees minus theta, therefore they are equal to each other. Repeat again. Angle MDC in the big triangle equals to angle MAB in the small triangle. They are both equal to 90 degrees minus theta, therefore they are equal to each other. So actually, we proved that all the three angles in the big triangle DMC are correspondingly equal to all the three angles in the small triangle A and B. Therefore, the big triangle DMC is similar to the small triangle A and B according to angle similarity rule. So write it down. The big triangle DMC is similar, this is the sign of similar, to the small triangle A and B according to angle similarity rule. What is angle similarity rule? Angle similarity rule is that if you prove that all the three angles in one triangle are correspondingly equal to all the three angles in another triangle, then you actually proved that the two triangles are similar to each other according to angle similarity rule, exactly as we proved in our two triangles. Okay, so from the fact that the two right triangles are similar to each other, we will conclude that the following relationship exists between their sides. Okay, we will conclude that MC in the big triangle over MB in the small triangle equals to DC in the big triangle over AB in the small triangle. Do it again. MC over MB equals to DC over AB. MC is very easy to see from the drawing that MC equals to MB plus BC, that is to say MC equals to MB plus BC, that is 8. In conclusion, we found out that MC equals to MB plus 8. So we substitute MC by MB plus 8. MC is MB plus 8 over MB. It is equal to DC is 8 over AB is 2. So we found out that MB plus 8 equals MB plus 8 over MB equals to 8 over 2. 8 over 2 is 4, so 4 equals to MB plus 8 over MB. We multiply this equation by MB, and finally we get that MB plus 8 equals to 4 times MB. Here we subtract MB from this equation, and finally we get that 8 equals to 4MB minus MB, it is 3MB. Here we divide this equation by 3, and finally we get that MB equals to 8 over 3 units. Here we can write down the original drawing. this side MB, it is equal to 8 over 3 units in its length. In the next step, we focus on the right triangle A and B. We will implement the Pythagoras theorem on this right triangle A and B. Here by PT is the abbreviation for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is AM, the square of the hypotenuse is AM squared. Is equal to AB squared plus MB squared. Repeat again. According to the Pythagoras theorem in the right triangle AMB, AM squared equals to AB squared plus MB squared. So AM squared equals to AB squared. AB is 2, therefore AB squared is 2 squared, that is 4, plus MB squared. We just found out that MB equals to 8 over 3, therefore MB squared equals to 8 over 3 squared. So AM squared equals to 4 plus 8 over 3 squared equals to 8 squared, that is 64, over 3 squared, that is 9. So AM squared equals to, here we multiply 4 by 9 and then we divide it by 9 in order to a common factor of 64 over 9. And we get that 4 times 9 is 36 plus 64 over 9. So AM squared equals to 36 plus 64, it is 100 over 9. Here we take a root out of this equation and finally we get that AM equals to the square root of 100 over 9. The square root of 100 is 10. The square root of 9 is 3. In conclusion, we found out that the length of line segment AM is 10 over 3 units. So we write it down here in the original drawing. The length of this line segment AM is equal to 10 over 3 units. In the next step, I will present to you a new rule and we will implement the new rule in our drawing. We have here rule number 1. According to rule number 1, the tangent to a circle is perpendicular to the radius drawn to its point of tendency. Tangent AB is tangent to this circle at point M. Point M is the point of tendency. You have the radius OM that is drawn to the point of tendency, that is to say it is drawn to point M, that is the point of tendency. Therefore, according to this rule, rule number 1, the tangent AB will be perpendicular to the radius MO. That is to say this angle equals to 90 degrees and this angle equals to 90 degrees according to this rule, rule number 1. So we can implement, so whenever you have a radius that is drawn to the point of tendency, then the tangent will be perpendicular to the radius. In this case, tangent AB equals to, tangent AB is perpendicular to MO, the radius MO, this angle equals to 90 degrees and this angle equals to 90 degrees. So we can implement rule number 1 in our drawing. We define the center of this circle as O. We define the point of tendency of tangent AB with this circle as M. We join points M and O together by straight line. Point O is the center of the circle, point M is the point of the circle itself. The point of the circle itself, therefore OM is the radius of the circle that we define as X. So the radius OM, it is drawn to point M, that is the point of tendency. Therefore, according to rule number 1, tangent AB will be perpendicular to the radius MO. That is to say, this angle equals to 90 degrees, and this angle will be equal to 90 degrees according to rule number 1. Likewise, we have tangent BC is tangent to this circle at this point. We'll define the point of tangency as N. We'll join points O and N together by a straight line. Again, point O is the center of the circle, point N is the point on the circle itself, therefore ON is the radius of the circle that we defined as X. We have the radius ON. The radius ON, it is drawn to the point of tendency, that is to say, it is drawn to point N. Therefore, tangent BC will be perpendicular to the radius NO. If BC is perpendicular to NO, it means that this angle equals to 90 degrees, and this angle equals to 90 degrees according to rule number 1. We'll focus on quadrilateral OMBN. This quadrilateral OMBN, we have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So 270 degrees plus 90 degrees, it is 360 degrees. In the next step, we draw perpendicular on BC in such a way that that perpendicular will be also tangent to this circle. So this angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular and BC is L. This is the point of tendency of the perpendicular with the circle. We define the point of tendency as point G. We join points G and O together by a straight line. Point O is the center of the circle, point G is the point on the circle itself, therefore OG is the radius of the circle that is equal to X. Again, we have the radius OG that is drawn to the point of tendency, that is to say it is drawn to point G, that is the point of tendency, and therefore of tangent LG with this circle. Therefore, according to rule number 1, the tangent LG will be perpendicular to the radius OG. That is to say, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 1. We'll focus on quadrilateral OGLN. In this quadrilateral there will be 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees according to the rule that I mentioned. Angle MOG, this angle equals to 90 degrees plus 90 degrees, that is 180 degrees. Any angle that is equal to 180 degrees must be a straight line. So the radius X is absolutely a straight line, the radius OG is absolutely a straight line, and here also MOG is also a straight line. So in total, MOG it is a straight line, because at the touching point of the two radii we have a straight line. Therefore in total MOG must be a straight line. If MOG is a straight line, then MG is also a straight line. But the straight line MG touches the circle at points M and G. Therefore, the straight line MG, it is a chord. It is a chord that passes through the center of the circle. Therefore, chord MG that passes through the center of the circle, that is to say for point O, must be the diameter of the circle. So I write it down. MG is the diameter of the circle. because it passes for the center of the circle. It is a chord that passes for the center of the circle. We'll focus on quadrilateral MGBL. Quadrilateral MGBL. Here we have 1, 2, 3, 4 right angles. Any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we'll write quadrilateral MGBL as a rectangle. The opposite sides of a rectangle are equal to each other. That is to say, side MG equals to side BL. MG equals to BL. But MG is the diameter of the circle. MG is the diameter of the circle. From this equation, we will derive that BL is also the diameter. BL is the diameter of the circle. And because of the fact that the radius of this circle equals to x according to our definition, the diameter must be twice as long as the radius. That is to say, the diameter of the circle BL must be equal to 2x. If we found out that the length for this line segment BL equals to 2x. So I write it down here. BL equals to 2x. In the next step, we will extend the perpendicular LG by a straight line until it touches side MD. And we will define the touching point of the extended LG and side DM as T. So in the next step, we will prove that the right triangle TML, the right big triangle TML, is similar to the small right triangle AMB. But first of all, we'll focus on the big right triangle TLM. On this big triangle TLM, this angle equals to theta. This angle equals to 90 degrees. Therefore, the missing angle here must be equal to 90 degrees minus theta. Okay, so we'll prove that the right triangle, the right big triangle TML similar to the small right triangle ABM. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. So we can write down that angle T and M in the big triangle is equal to this angle ABM, the small triangle. So both equal to 90 degrees, therefore they are equal to each other. Repeat again. Angle TLM in the big triangle equals to angle ABM in the small triangle. They are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle theta, that is a common angle that belongs to both triangles, therefore angle theta equals to itself. We can define angle theta, we can call to angle theta two different names. Angle theta is equal to angle TML. TML. It is equal to itself. Angle theta can be defined also as angle AML, AMB. When we relate to it, it belongs to the small triangle, AMB. repeat again. Angle theta, it is angle TML, and it is equal to angle theta itself, that is angle, we can call it also angle A and B. So angle theta equals to itself, is the common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. So I write it down. This is angle LTM, and it is equal to this angle that is this is the big triangle, and it is equal to angle BAM in the small triangle. They are both equal to 90 degrees minus theta, therefore they are equal to each other. Repeat again. Angle LTM in the big triangle equals to angle BM in the small triangle. They are both equal to 90 degrees minus theta, therefore they are equal to each other. So we actually prove that all the three angles in the big triangle are correspondingly equal to all the three angles in the small triangle. So we actually prove that the big triangle TML is similar, this is the sign of similar, to the small triangle ABM, according to angle similarity rule. And from the fact that the two right triangles are similar to each other, we conclude that the following relationship exists between their sides. That ML in the big triangle over MB in the small triangle equals to TL in the big triangle over AB in the small triangle. I'll repeat again. I conclude that ML over MB equals to TL over AB. Here ML equals to MB plus BL, that is to say ML equals to MB, that is 8 over 3 plus BL, that is 2x. So in total ML equals to 8 over 3 plus 2x. So that ML by 8 over 3 plus 2x over MB is 8 over 3. And it is equal to TL. TL is the missing side, so we leave it as it is. Over AB is 2, so we solve it AB by 2. In conclusion, we found out that 8 over 3 plus 2x over 8 over 3 equals to TL over 2. Here we'll multiply 2x by 3, and then we'll divide it by 3 in order to have a common factor of 8 over 3. And finally we get that 8 over 3 and 2x times 3 is 6x, so it is 6x over 3 divided by 8 over 3 equals to TL over 2. So here we have 8 in the numerator and 8 in the denominator, so 3 in the numerator and 3 in the denominator, so 3 will get cancelled, and finally we get that 8 plus 6x over 8 equals to TL over 2. We cross multiply this equation and we get that 2 times 8 plus 6x equals to 8 times TL, Here we'll divide this equation by 2 and finally we get that 8 plus 6x equals to 8 over 2 is 4. So in total this expression equals to 4TL. Here we divide this equation by 4 and finally we get that TL, the missing side, equals to 8 over 4 is 2 and 6x over 4 is 1.5x. In conclusion, we found out that TL equals to 2 plus 1.5x, so we can write down in the original drawing. The TL, this line segment TL, equals to 2 plus 1.5x. So because of the fact that triangle MTL is similar to the small triangle AMMB, we can conclude that addition relationship exists between their sides. We conclude that ML in the big triangle over MB the small triangle equals to TM in the big triangle over AM in the small triangle. Repeat again. We conclude that ML over MB equals to TM over MA. So ML equals to 8 over 3 plus 2x over MB, that is 8 over 3, is equal to TM. TM equals to MA plus AT, that is to say MA is 8 over 3 plus AT. So in total MT equals to 8 over 3 plus AT. 8 over 3 plus AT over AM. AM is 8 over 3. In the next step, we'll multiply 2x by 3 and then we'll divide it by 3 in order to overcome a factor of 8 over 3. So we have 8 over 3, 2x times 3 is 6x. We have 6x over 3 over 8 over 3 is equal to, here we multiply 80 by 3 and then we divide it by 3 in order to overcome a factor with 8 over 3. So we have 8 plus 80 times 3 is 380 over 3 over 8 over 3. Okay, so here in this side of the equation we have 3 in the numerator and 3 in the denominator, so 3 will get cancelled. Here also we have 3 in the numerator and 3 in the denominator, so 3 will get cancelled. And finally, after we cancel 3, we are left with 8 plus 6x over 8. It is equal to 10 plus 380 over 10. So here we first multiply this equation and finally we get that 10 times 8 plus 6x equals to 8 times 10 plus 380. Here we'll open the brackets on both sides of this equation and we get that 10 times 8 is 80 plus 10 times 6x is 60x and is equal to 8 times 10 is 80 plus 8 times 380 is 2480. So here we have 80 in both sides of the equation, so 80 will get cancelled, and we're left only with 60x, that is equal to 2480. Here we divide this equation by 24, and finally we get that 60x over 24 is 2.5x. So in total we found out that 80 equals to 2.5x, so we can write down in the original drawing that 80 equals to 2.5x. Yeah, 80 equals to 2.5x. In the next step, I will copy quadrilateral ATLB in a new page and we will analyze it. So actually, this is quadrilateral ATBL, this is a code from the original drawing. Inside this quadrilateral ATBL, we have this circle that is blocked by the quadrilateral, so I'll copy this circle here. This circle is point to this quadrilateral, is tangent to this quadrilateral at 4 points. This is the first point of tendency. We'll define the point of tendency as M. The second point of tendency is here. We'll define this point as N. This is the third point of tendency. We'll define this point as K. And finally, this is the fourth point of tendency between the quadrilateral and the circle. So we'll define this point as L. So in the next step, I present to you a new rule and we will implement the new rule number 2 in our drawing. According to rule number 2, we have the lengths of two tangents from a common external point to a circle are equal. We have the common external point, point P. From the common external point, point P, we have two tangents to this circle. Tangent PA is tangent to this circle, point A, and tangent PB is tangent to this circle, point B. According to rule number 2, whenever we draw from a common external point two tangents to the circle, the lengths of two tangents must be equal to each other. In this case, tangent PA equals to tangent PB. We can implement rule number 2 in our drawing. Why? Because in our drawing, we have, if we focus at point A, point A is the common external point. From the common external point, point A, we have two tangents to this circle, tangent AM and tangent AN. And according to rule number 2, AM equals to AN. So if AM is A, then AN must be also equal to A. The next step we focus on the common external point, point B. From the common external point, point B, we have two tangents to this circle, tangent BK and tangent BN, and according to rule number 2, tangent BN must be equal to tangent BK. So if BN is B, then BK must be also equal to B. We focus on the common external point L. We find the touching point, the point of tendency. Here we have two same letters, so I define it as G. So from the common external point L, we have this point. We have two tangents to this circle, tangent LK and tangent LD. And according to 1 over 2, tangent LK must be equal to tangent LG. Those two tangents must be equal to each other, so if KL is C, then GL must be also equal to C. Finally, we focus on the common external point T. On the common external point T, we have two tangents to this circle, tangent TM and tangent TG, and according to 1 over 2, tangent TM must be equal to tangent TG. That is to say, if TM equals to D, then TG must be also equal to D. In the next step, we'll join side AT with side BL. We call the other AT BL. Okay, so here, side AT plus side BL is equal to AT is A plus D. AT is A plus D, so we substitute AT by A plus D. Plus BL. On the drawing, it is very easy to see that BL equals to B plus C, so we substitute BL by B plus C. In conclusion, we found out that AT plus BL equals to A plus D plus B plus C. So you can change the orders of the letters here, and it will be A plus B plus C plus D. In the next step, we join side AB with side TL, we call the other ATBL. So AB plus TL is equal to AB equals to A plus B, so substitute AB by A plus B, and TL is D plus C, so substitute TL by D plus C. So in conclusion, we found out that AT plus TL equals to A plus B plus C plus D, and AT plus TL equals to A plus B plus C plus D, and AB plus D equals to A plus B plus C plus D, and AT plus BL also equals to A plus B plus C plus D. That is to say, those two expressions are equal to each other. So we can write down that AT plus BL equals to AB plus TL AT equals to 2.5x, so result is AT by 2.5x plus BL. Here, BL equals to 2x, so we substitute VL by 2x. And it is equal to AB. AB is 2, so we substitute AB by 2. And finally plus TL. TL equals to 2 plus 1.5x, so we substitute TL by 2 plus 1.5x. So in conclusion, we found out that 2.5x plus 2x equals to 2 plus 2 plus 1.5x. 2.5x plus 2x is 4.5x, and is equal to 2 plus 2, that is 4, plus 1.5x. Here we subtract 1.5x from this equation, and finally we get that 4.5x minus 1.5x, it is 3x, is equal to 4. Here we divide this equation by 3, and finally we get that x equals to 4 over 3 units. That is to say, the radius x of this circle equals to 4 over 3 units. And the area of any circle, here the square brackets is the sign for the area. The area of any circle equals to pi times the radius squared. In our case, it is pi times x squared. And x equals to 4 over 3. Therefore, we substitute x by 4 over 3. So it is pi times x is 4 over 3. If x is 4 over 3, then x squared is 4 over 3 squared. So in conclusion, we found out that the area of our circle equals to pi times 4 over 3 squared. 4 over 3 squared is 4 squared, that is 16. Over 3 squared, that is 9. So the area of this circle equals to either 16 pi over 9 square units, or in terms of numbers, it is equal to 5.585 units. So repeat again, the area of this circle equals to either 16 pi over 9 square units, or in terms of numbers, it is equal to 5.585 units, 5 square units. Okay, so in the next step, I'll summarize the lecture. In this lecture, we found out the area of this circle. In the drawing, we have quadrilateral ABCD. You know that side AB equals to 2 units in its length, side BC equals to 8 units in its length, side DC equals to 8 units also in its length. This angle ABC equals to 90 degrees, and this angle DCB equals to 90 degrees. Our mission is to find out the area of this circle. So first of all, we did a construction. We extended side DA and side CB until they touch each other at point. We define the touching point of the two sides. Of the two extended sides is point M. CB is one side of the quadrilateral, therefore it is absolutely a straight line. When we extended CB by straight line, the result is CM. When you extend a straight line by straight line, the result must be a straight line. So CM is also a straight line. CM is a straight line. So if you focus on the upper side of the straight line CM at point B, the sum of the angles must be equal to 180 degrees according to the rule that the sum of the angles and the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of CM at point B? We have this angle that is 90 degrees. Therefore, the missing angle must be also equal to 90 degrees. In order to complete the sum of the angles on the upper side of CM at point B to 180 degrees, the missing angle must be equal to 90 degrees. So angle ABM equals to 90 degrees. We define this angle as theta, and the small triangle MAB this angle equals to theta. This angle equals to 90 degrees, therefore the missing angle here must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, we focus on the big triangle DMC. The big triangle DMC, this angle equals to theta. This angle equals to 90 degrees, therefore the missing angle must be equal to 90 degrees minus theta. Then we prove that the big triangle MDC is similar to the small triangle MAB. Why the two triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, this angle theta, it is a common angle that belongs to both triangles, that is to say angle theta equals to itself. And finally, those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. So we actually prove that all the three angles in the big triangle MDC are correspondingly equal to all the three angles in the small triangle MAB. Therefore, those two triangles are similar to each other according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we conclude that the following relationship exists between their sides. We conclude that MC in the big triangle over MB in the small triangle equals to DC in the big triangle over AB in the small triangle. I'll repeat again. MC over MB equals to DC over AB. MC equals to MB plus BC. That is to say, MC equals to MB, that is unknown, plus BC, that is 8. So in total, MC equals to MB plus 8. Therefore, we substitute MC here by MB plus 8. So it is MC it is MB plus 8 over MB equals to DC. DC is 8 and AB is 2. So DC over AB is 8 over 2. 8 over 2 is 4. So MB plus 8 over MB equals to 4. We multiply this equation by MB. And finally we found out that 4 times MB equals to MB plus 8. Then we subtracted MB from this equation and finally found out that 8 equals to 4MB minus MB, it is 3MB. So 8 equals to 3MB. We divided this equation by 3 and finally found out that MB equals to 8 over 3 units. This side MB equals to 8 over 3 units. Then we implemented the Pythagoras theorem on the right triangle A and B. According to the Pythagoras theorem, in the right triangle A and B, the square of the quadrant equals to the sum of the squares of the perpendiculars, that is to say AM square equals to AB square plus BM square. Repeat again. In the right triangle A and B, according to the Pythagoras theorem, AM square equals to AB square plus MB square. So AM square equals to AB square. AB is 2, so AB square is 2 square, that is 4, plus MB square. MB is 8 over 3, therefore MB square is 8 over 3 square. So AM square equals to 4 plus 8 over 3 square equals to 8 square, that is 64, over 3 square, that is 9. So in conclusion, found out that AM square equals to 4 plus 64 over 9. Then we multiplied 4 by 9 and then we divided by 9 in order to overcome factor with 64 over 9. 4 times 9 is 63, so it is 63 plus, it is 36. 4 times 9 is 36, so it is 36 plus 64 over 9. So 36 plus 64, it is 100, so it is 100 over 9. AM square equals to 100 over 9. We took out of this equation and found out that AM equals to the square root of 100 over 9, that is 10 over 3. So we found out that AM equals to 10 over 3 units. In the next step, I presented to you a new rule and we implemented the new rule in our drawing. according to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. Tangent AB is tangent to this circle is point M. Point M is the point of tendency. And we have the radius OM that is drawn to the point of tendency, that is to say it is drawn to point M. And whenever we have a radius that is drawn to the point of tendency, then the tangent AB will be perpendicular to the radius MO. So if AB is perpendicular to MO, it means that this angle equals to 90 degrees and this angle equals to 90 degrees according to this rule, rule number 1. We can implement rule number 1 in our drawing. We define the center of this circle as O. Tangent AB is tangent to this circle is point M. We have point O is the center of the circle, point M is the point of the circle itself, therefore OM is the radius of this circle. The radius OM, we define the radius of this circle OM as X. The radius OM, it is drawn to point M, that is the point of tendency. Therefore, according to rule number 1, tangent AB will be perpendicular to the radius MO. So if AB is perpendicular to MO, it means that this angle equals to 90 degrees and this angle equals to 90 degrees according to rule number 1. And here we joined tangent BL is tangent to the circle is point N. We have the radius ON that is drawn to the point of tendency, that is to say it is drawn to point N, therefore according to rule number 1, tangent BL will be perpendicular to the radius ON, that is to say this angle equals to 90 degrees and this angle equals to 90 degrees according to rule number 1. So in quadrilateral MOBN we have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees. According to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Okay. Then we did the construction, that is to say we draw perpendicular on BC. Okay. So this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We do this perpendicular GL in such a way that it will be also tangent to the circle. It is absolutely possible to do it. So here LG is tangent to this circle as point G. The radius OG is drawn to the point of tendency. That is to say it is drawn to point G, that is the point of tendency. Therefore, this angle equals to 90 degrees and this angle equals to 90 degrees according to rule number 1. So in quadrilateral OG and E and OG and L, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees according to the rules that I mentioned. So we have here line segment MG. Angle MOG equals to 280 degrees. 90 plus 90 is 180. So angle MOG equals to 180 degrees. Any angle that is equal to 180 degrees, it is a straight line. Therefore, MOG is a straight line. But MOG touches the circle at 2 points. It's point M and at point G. Therefore, MOG, it is actually chord. MG is a chord that passes through the center of the circle. That is to say, it passes for point O, that is the center of the circle. Any chord that passes through the center of the circle must be the diameter of the circle. Therefore, line segment MG must be the diameter of the circle. Okay, MG is the diameter. So we focus on quadrilateral MGBL. Inside this quadrilateral we have 1, 2, 3, 4 right angles. Any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we relate to quadrilateral MBGL as a rectangle. The opposite sides of a rectangle are equal to each other. That is to say, side MG equals to side BL. Okay. Yeah. side MG equals to side BL. But MG is the diameter of the circle, so you can write it that MG is the diameter. And from this equation, the diameter equals to MG equals to BL, we will derive that BL, it is also the diameter of the circle. Here BL is the diameter of the circle. But the radius of the circle is equal to x according to our definition. Therefore, the diameter must be twice as long as the radius. That is to say, the radius BL must be equal to 2x. So BL equals to 2x. So in the next step, we extended the perpendicular LG until it touches the circle, until it touches the side DM at point T. Then we proved that the big right triangle TLM is similar to the small triangle ABM. First of all, in the big triangle TLM, this angle equals to theta, this angle equals to 90 degrees, therefore this angle must be equal to 90 degrees minus theta according to what I've already explained. Then we proved that the big triangle TLM is similar to the small triangle ABM. Why those two triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, this angle theta, it is angle, this common angle, it belongs to both triangles, so angle theta equals to itself. And finally, those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. So I actually proved that all the three angles of the big triangle TLM are correspondingly equal to all the three angles of the small triangle ABM. Therefore, the two triangles are similar to each other according to angle similarity rule. And from the fact that those two triangles are similar to each other, we conclude that the following relationship exists between their sides. That ML in the big triangle over MB in the small triangle equals to TL in the big triangle over AB in the small triangle. I'll repeat again. ML over MB equals to TL over AB. I said again that ML is 8 over 3 plus 2x. ML is 8 over 3 plus 2x. MB is 8 over 3. TL is the missing side, and AB equals to 2 according to what is given us in the question. Here we multiply 2x by 3 and then we divide it by 3. 2x times 3 is 6x, so here we will have 6x plus 8 over 3 over 8 over 3 equals to TL over 2. We have 3 in the numerator and 3 in the denominator, so 3 will get cancelled, and we get that 8 plus 6x over 8 equals to TL over 2. Here we cross multiply this equation, and finally we get that 2 times 8 plus 6x equals to 8 times TL. We divided this equation by 2, and finally we get that 8 plus 6x equals to 8TL over 2 is 4TL. So 8 plus 6x equals to 4TL. We divided this equation by 4, and finally we found out that TL equals to 8 over 4 is 2, and 6x over 4 is 1.5x. In conclusion, we found out that TL equals to 2 plus 1.5x. Here, this line segment TL equals to 2 plus 1.5x. Here, because of the fact that triangle TML is similar to triangle ABM, we can conclude that another relationship exists between their sides. We conclude that ML in the big triangle over MB in the small triangle equals to TM in the big triangle over AM in the small triangle. I'll repeat again. ML over MB equals to TM over MA. Here, ML, we already found out that ML equals to 8 over 3 over 2x. Here, ML equals to 8 over 3 plus 2x. MB equals to 8 over 3. TM, what is the size of TM, the length of TM? TM, from the law it is already to say that TM equals to 8 over 3 plus 80. Again, TM equals to 8 over 3 plus 80. So substitute TM by 8 over 3 plus 80, and over AM is 8 over 3. So we substitute AM by 8 over 3. Then we multiplied 2x by 3, and then we divided by 3, multiplied 80 by 3, and then we divided by 3. 2x times 3 is 6x, so we have 8 plus 6x over 3, over 8 over 3, and 80 times 3 is 380, plus 10 over 3, over 10 over 3. So we have 3 in the numerator and 3 in the denominator, so 3 will get cancelled. We have 3 in the numerator and 3 in the denominator, so 3 will also get cancelled. And finally we found out that 8 plus 6x over 8 equals to 10 plus 380 over 10. Then we cross multiply this equation and found out that 10 times 8 plus 6x equals to 8 times 8 plus 380. Then we open the brackets on both sides of this equation and found out that 10 times 8 is 80 and 10 times 6x is 60x. It is equals to 8 times 10 is 80 plus 10 plus 10 times 380 is 2480. We have 80 on both sides of the equation, so 80 will get cancelled. And we left only with 60x, that is equal to 2480. We divided this equation by 24 and finally found out that 80 equals to 60x over 24, it is 2.5x. So we found out that the length of this line segment 80, it is equal to 2.5x. Then I copied quadrangle ATBL in a new page and analyze this quadrangle. This is quadrangle ATBL that I copied from the original domain. Inside this quadrangle, we have this circle that is blocked by the quadrangle, so I copied also this circle and I presented to you rule number 2. According to rule number 2, the lengths of two tangents from a common external point to a circle are equal. We have the common external point P. From the common external point P, we have tangent PA and tangent PB. According to this rule number 2, the lengths of those two tangents that are extended from the common external point must be equal to each other. That is to say, tangent PA equals to tangent PB in its length. You can implement rule number 2 in our drawing. This circle has 4 tangents. It's tangent to the quadrangle ATBL in 4 points. This is the first point of tangency that we defined as M. The second point of tangency we defined as N. The third point of tangency we defined as K. And the fourth point of tangency we defined as G. Then, if we focus on point A, from the common external point A, we have 2 tangents to this circle, tangent AM and tangent AN, and according to rule number 2, they must be equal to each other. That is to say, AM equals to AN. So if AM is A, then AN must be also equal to A. Okay. Then we focus on the common external point B. From the common external point B, we have 2 tangents to this circle, tangent BK and tangent BN. And according to rule number 2, they must be equal to each other. So BK equals to BK equals to Bn. So if BK is B, then Bn must be also equal to B. Then focus on the common external point L. From the common external point L, we have 2 tangents to this circle, tangent LK and tangent LG. And according to rule number 2, the lengths of those 2 tangents must be equal to each other. That is to say, LK equals to LG. LK equals to LG. So if LK is C, then LG must be also equal to C. And finally, focused on the common external point P. From the common external point P, we have 2 tangents to this circle, tangent TM and tangent TG. According to rule number 2, the 2 tangents must be equal to each other. That is to say, TM equals to TG. So if TM is D, then TG must be also equal to D. And then we added side AT with side BL in quadrangle AT-BL. AT plus BL. AT is A plus D, so we substitute AT by A plus D. And BL is B plus C, so we substitute BL by B plus C. In conclusion, found out that AT plus BL equals to A plus D plus B plus C. That is actually, if you change the order, we get that AT plus BL equals to A plus B plus C plus D. In the next step, we added side AB to side TL of quadrilateral ATBL. AB is A plus B and TL is C plus D. So in total, AB plus TL is A plus B plus C plus D. Again, AB plus TL is A plus B plus C plus D. So AT plus BL equals to A plus C plus D. And then AB plus TL also equals to A plus B plus C plus D. Therefore, they must be equal to each other. That is to say, AT plus BL must be equal to AB plus TL. Okay? So AT is 2.5x. So substitute AT by 2.5x. BL is 2x, so substitute BL by 2x. And it is equal to AB, that is 2, so we substitute AB by 2, and plus TL. TL is 2 plus 1.5x, so we substitute TL by 2.5x. And finally we found out that AT plus BL that is equal to AB plus TL, it is actually 2.5x plus 2x equals to 2 plus 2 plus 1.5x. 2.5x plus 2x is 4.5x. 2 plus 2 is 4. So in total, this is the equation, we have 4 plus 1.5x. Then we subtracted 1.5x from this equation, and finally found out that 4.5x minus 1.5x is this 3x, that is equal to 4. Then we divided this equation by 3, and finally found out that x equals to 4 over 3 units. X is the radius of this circle, that is equal to 4 over 3 units. The radius of this of any circle, this is the sign for the area. The area of any circle equals to pi times the radius square. In our specific circle, the radius r equals to x. Therefore, pi r square, it is actually pi x square. X, we just found out that x equals to 4 over 3, so we can substitute x by 4 over 3. If x is 4 over 3, then x squared is 4 over 3 squared. So pi times 4 over 3 squared. 4 over 3 squared is 4 squared, that is 16, over 3 squared, that is 9. So we found out that the area of this circle equals to either 16 pi over 9 square units, or in terms of numbers, it is equal to 5.585 square units. Okay, thank you very much.